After studying this module, you shall be able to understand the Kruskal-Wallis model, learn the testing procedures of Kruskal-Wallis model, know about post hoc equal groups and unequal groups, understand the Friedman's test. The single factor ANOVA compares population mean for n number of independent groups. The normality assumption is required for one factor ANOVA. But if our data is not normally distributed, we can use Kruskal-Wallis test for comparing population mean, provided that all of them have a similar distribution. This is much less strict assumption in comparison to the normality assumption, and the same distribution assumption can be tested using Kolmogorov-Smirnov test discussed in the previous model. For example, you could use a Kruskal-Wallis test to understand whether exam performance measured on a continuous scale from 0 to 100 differed based on family income level. That is, your dependent variable would be exam performance and your independent variable would be family income level, which has three independent groups: students with low, medium and high family income levels. In case of more than one factor, we can use Friedman's test. Kruskal-Wallis test is an omnibus test statistic like one factor ANOVA and can tell you only that all population means are same or not. It cannot tell you which specific population mean is statistically significant, different from which population mean. Since with multiple groups we would be interested in knowing the same, this can be done using a post hoc analysis, to be discussed later in this module. Data should satisfy following characteristics for Kruskal-Wallis test to be applicable. 1. The dependent variable should be measured at the ordinal or continuous scale. 2. Dependent variable should be measured for two or more than two independent groups. 3. The distribution of dependent variable in the independent group must be same as discussed above. And 4. The dependent variable must be independent, implying that it must not be related to observation within the group or with the observation in other group. Test procedures. Let the number of samples be I. Xij denotes the jth observation from ith sample. N is the total number of observation in all the samples. H naught is mu1 is equal to mu2 is equal to mu3 till mu I. We rank all observations from 1 to n in increasing order. The idea behind the test is that when H naught is true, the assignments of rank 1, 2 to n to the j samples are equally likely and we expect ranks to intermingled. But when H naught is not true, then some of the samples would be giving mostly smaller ranks and other samples will mostly higher ranks. Let Rij denote the rank of jth observation from ith sample. Ri is equal to sigma j from 1 to ni, Rij divided by ni. R is equal to n plus 1 divided by 2. K is equal to sigma I from 1 to g ni in brackets r minus ri square divided by sigma I 1 to g sigma j 1 to ni rij minus r whole square. If the data contain no ties, the denominator of the expression for k would be n minus 1 into n plus 1 divided by 12, and that gives k is equal to 12 by n plus 1 sigma I from 1 to g ni into ri minus n plus 1 divided by 2 whole square is equal to 12 divided by n into n plus 1 sigma I from 1 to g ni ri square minus 3 into n plus 1. When H naught is true and either I is equal to 3, j is greater than equal to 6, I is equal to 1, 2, 3, I is greater than equal to 3, j is greater than equal to 6 for I is equal to 1, 2, 3 till capital I. The k has approximately a chi-squared distribution with I minus 1 degree of freedom. In such cases, usual chi-square critical values can be used to test H naught at appropriate significance level. Let's look at an example. Does physical exercise affect depression? To test this, we found some depressed people and checked that they are all equivalently depressed to begin with. then we allocate each person randomly to one of the three groups: no exercise, 20 minutes of jogging per day, or 40 minutes of jogging per day. At the end of the month, we ask each participant to rate how depressed he or she now feels. On a Likert scale, and that runs from 1, which is totally miserable, through 200, ecstatically happy. Of no exercise, jogging for 20 minutes, and 40 minutes, as you can see. H naught is equal to mu1 is equal to mu2 is equal to mu3. N is 24, Ri is 9.5, 10 and 18 for no exercise, jogging for 20 minutes and jogging for 40 minutes respectively. R1 is equal to 9.5, R2 is equal to 10 and R3 is equal to 18. Sigma I is equal to 1 to G, Ni Ri square is equal to 8 into 9.5 square plus 8 into 10 square plus 8 into 18 square, which is 4141. K is equal to 12 divided by N into N plus 1, sigma I from 1 to G, Ni Ri square minus 3 into N plus 1, which is equal to 7.29. The degree of freedom is 1 less than the number of group, that is 2. The critical value of chi square at 2 degrees of freedom is 5.99 at 0.05 level of significance. Since the calculated value is higher than the critical value, we reject the null hypothesis and we conclude that jogging significantly affects stress level. Let's look at another example. Create two different normal probability distribution objects. The first distribution has mu is equal to 0, sigma is equal to 1. Second distribution has 2 sigma is equal to 1. Create a data set containing 3 variables. The first 2 columns of data set contain data generated from the first distribution, while the third column contains data generated from the second distribution. The data is given in table 1 of appendix. Our objective is to test the null hypothesis that the sample data from each column in X comes from the same distribution. Let's look at the solution now. Pearson chi-square, which is equal to 19.6, which is higher than the critical and the null hypothesis, is rejected. Figure 1 gives box plot of 3 variables, and from the box plot we can see that third variable certainly has different distribution. We know that it came from a normal probability distribution with mu is equal to 2, sigma is equal to 1, while the first 2 came from second distribution, 0, sigma is equal to 1. If you look at the box plot, the blue plot basically describes the column 1, pink column 2 and green column 3. Post hoc equal groups. The post hoc analysis is dependent on the size of the independent groups. Equal groups. We calculate pairwise K statistics using the formula given below. K is equal to D minus 0.8 divided by N into root N. D is equal to R1 into N minus R2 into N. If the calculated value of K is greater than the critical values given in table 3 in appendix, for chosen significance level, we reject the null hypothesis. Continuing with our example, we compare no jogging with 20 minutes of jogging. H naught is equal to mu1 is equal to mu2. D is equal to 10 into 8 minus 9.5 into 8, which is equal to 4. K is equal to 4 minus 0.8 divided by 8 into root 8, which is equal to 0.14. Since the calculated value is less than the critical value of 2.8 for 3 groups, we could not reject the null. Next, we compare no jogging with 40 minutes of jogging. H naught here will be mu1 is equal to mu3. D will be 18 into 8 minus 9.5 into 8 is equal to 68. K will be 68 minus 0.8 divided by 8 into root 8, which is 2.97. Since the calculated value is greater than the critical value of 2.89 for 3 groups, we can reject the null. Next, we compare 20 minutes of jogging with 40 minutes of jogging. Now the null becomes mu2 is equal to mu3. D is 18 into 8 minus 10 into 8, which is 64. And K is 64 minus 0.8 divided by 8 into root 8, which is 2.79. Since the calculated value is less than the critical value of 2.89, for 3 groups, we couldn't reject the null. Post hoc unequal groups. In case of unequal groups, one can use the Wilcoxon rank sum test on each pair of groups and adjust the p-value with the Bonferroni method. Bonferroni adjustment is required as a load of paired tests without some adjustment is likely to cause type 1 error. For simple Bonferroni adjustment, you divide the p-value to be achieved for significance by the number of paired comparisons to be made. So if you have 3 groups and the overall test of significance between them comes out significant using 5% threshold value, you might want to compare all the pairs to see which are significantly different. In case of k independent groups, the number of paired comparison to be done is k into k minus 1 divided by 2. In case of 3 independent groups, this comes out to be 3 into 2 divided by 2, which is 3. So any pair has to achieve a p-value of less than 0.05 divided by 3, which is 0.017, to be significant at the 5% level. With 4 groups, number of paired comparison to be done is 4 into 3 divided by 2 equal to 6. So P for any pair has to be smaller than 0.05 divided by 6, which is 0.0083, to be significant. Let's look at another example. Table gives the efficiency of a chemical process using 3 different catalysts, A, B and C, on each of 4 days. Is there evidence that the different catalysts result in different efficiencies? We'll set up the null hypothesis, which is mu1 is equal to mu2 is equal to mu3. K here is calculated as 12 divided by n into n plus 1, sigma I from 1 to g, ni into ri square minus 3 into n plus 1, which is equal to 2. The degree of freedom is 1 less than the number of group, that is 2. The critical value of chi square at 2 degrees of freedom is 5.99 at 5% level. Since the calculated value is less than the critical value, we couldn't reject the null hypothesis. Since we couldn't reject the null hypothesis, there is no point of doing post hoc analysis. Friedman's test. It is assumed that within each sample, that is catalyst category, every sample item is recorded in the exactly same condition, that is, day doesn't affect. Now suppose day also affect. This is the situation similar to 2-factor ANOVA, and now if we are interested in whether different catalysts result in different efficiencies, we have to control for the effective day. This can be done using the famous Friedman's test. The Friedman's test statistics is given by F is equal to 12 divided by CR into R plus 1 sigma Wi square minus 3C into R plus 1 brackets, where C is the number of columns, R is the number of rows, Wi is the row-wise sum of ranks. F is approximately a chi-square distribution with R minus 1 degree of freedom. In such cases, usual chi-square critical values can be used to test the null at appropriate significance level. We can also test whether different days have different efficiencies after controlling for the effective catalyst by transposing the table. Example 4. Data in the table below gives the efficiency of a chemical process using 3 different catalysts, A, B and C, on each of 4 days. is there evidence that the different catalysts result in different efficiencies after controlling for the day? Now we will control for the day and ranks would be given for each day based on efficiency. If you look at, you can see the ranks given. F is equal to 12 divided by CR into R plus 1 sigma WI square minus 3C into R plus 1. C here is 4, R is 3, sigma WI square is 218 and F is 6.5. The degree of freedom is 1 less than the number of rows, that is 2. The critical value of chi-square at 2 degrees of freedom is 5.99 at 5% level of significance. Since the calculated value is higher than the critical value, we reject the null hypothesis and we can conclude that catalyst affects efficiency after controlling for the day. Suppose we are interested in testing whether day affects efficiency, we will create a transpose of the given table and ranks would be given for each catalyst. As you can see, this is the transpose of the given table. F here is 7.4 because C is 3, R is 4, sigma WI square is 262. The degree of freedom is 1 less than the number of rows, that is 3. The critical value of chi-square at 3 degrees of freedom is 7.81 at 5% level. Since the calculated value is less than the critical value, we couldn't reject the null hypothesis and we can conclude that day doesn't affect efficiency after controlling for the catalyst. Let's look at another example now. The fungi species richness was measured on a 10-point scale on 4 different species of trees over a period of 3 days and the results tabulated as below. You have day 1, day 2, day 3 as columns and tree 1, tree 2, tree 3 and tree 4 as rows. Perform a Kruskal-Wallace test to investigate whether there is a significant difference in fungi species richness between the trees. Take the measurement on different days as being replicate measurements. What do we have to do? First, we give the ranks to the fungi richness and we arrange it by tree and the same is given in table. So if you could see, ranks have been assigned. Kruskal-Wallace test statistics, K is equal to 12 divided by N into N plus 1, sigma I is equal to 1 to G, Ni Ri square minus 3 into N plus 1. The value of K is equal to 0.904, which is less than the value in table at 3 degrees of freedom, and thus we couldn't reject the null hypothesis. We can thus conclude that weeds per meter don't affect the corn out in statistical significant manner. Suppose in the example we are interested in exploring the significant difference in fungi species richness between the trees after controlling for the effect of the day. And then we have to conduct a Friedman's test as suggested. Now the ranks would be given column wise and the resulting rank table would look like this. The Friedman's test statistic is given by F is equal to 12 divided by CR into R plus 1, sigma WI square minus 3C into R plus 1. C is 3, R is 4, sigma WI square is 258. F is equal to 6.6. The degree of freedom is 1 less than the number of rows, that is 3. The critical value of chi-square at 3 degrees of freedom is 7.81 at 0.05 level of significance. Since the calculated value is less than the critical value, we couldn't reject the null hypothesis and we can conclude that there is no significant difference in fungi species richness between the trees even after controlling for the effect of the day. Example 6. Lamb's quarter is a common weed that interferes with the growth of corn. A farmer is interested in knowing that whether it affects the yield significantly. For thus he plants corn at the same rate in 16 small plots of ground and then randomly assigned the plots to 4 groups. He then weeded the plots by hand to allow a fixed number of lamb's quarter plants in each corn plot. These numbers were 0, 1, 3 and 9 in the 4 groups of plots. No other weeds were allowed to grow and all plots received identical treatment except for the weeds. Yields of corn quintal per acre in each of the plots are given in table below. Perform a Kruskal-Wallace test to rest the farmer's claim. So you have weeds in one column per meter, corn, weeds, corn, weeds. First, we give the ranks to the corn output and we arrange it by weeds per meter, and the same is given in table. So if you look, rank has been assigned. Kruskal-Wallace test statistics. K is equal to 12 divided by n into n plus 1, sigma I going from 1 to g, ni ri square minus 3 into n plus 1. The value of K is 5.56, which is less than the value in table at 3 degrees of freedom, and thus we couldn't reject the null hypothesis. We can thus conclude that weeds per meter don't affect the corn out in statistical significant manner. In this module, we have learned the Kruskal-Wallace test, the non-parametric equivalence of conventional single-factor ANOVA test. Kruskal-Wallace test should be used instead of single-factor ANOVA if your data is not normally distributed. These tests are useful in biostatistics and other areas where the data obtained is not normally distributed. We have also learned Friedman's test, which is the counterpart of parametric two-factor ANOVA.